slightly more difficult, but not long. So let's just briefly remind what we did. So we considered continuous symmetries. So continuous symmetry. Let's tell it what it is. So in the way we formulate it, this is one parameter family of diffeomorphisms. Which we call HS. So it's from configuration space to configuration space, which is our n-dimensional manifold. And here one parameter means that S is a parameter. So S is usually a real parameter or can be angle in application we had. So it should be continuous. So we should differentiate it, and it should be more than continuous because we took derivative with respect to S. So we also assume that which is smooth with respect to S as well. So it's differentiable with respect to S at least. And satisfies two properties. So first property is that properties of the composition. So the composition of the two is the so they have this additive property, right? So the composition is H of S plus 1 plus 2. And another property is that it does not change Lagrangian function. So Lagrangian function remains exactly the same. If you change coordinates, so it's exactly the same, which if you change coordinates S Q prime equal H S Q, and the velocity is changed in a standard way for the Jacobian matrix. So these two properties. So from this we have a theorem of Noether, which tells that continuous symmetry implies the conservation of the quantity which you can define as C, T, Q, Q dot. So general quantity C, which is defined for the Lagrangian function. So it's just a sum of all components or derivative of Lagrangian with respect to the velocities by the derivative of the symmetry with respect to its parameter taken at 0. So this is conserved, which means that it's constant along the, that means that it's constant for any solution. For any solution of the Euler-Lagrange equations. So that's what we did last time, and we found that there are two fundamental quantities which are conserved in this way. In mechanics, it's momentum, linear momentum, and angular momentum. Okay, so today we need to generalize. We will generalize this theorem. So it will take a generalized form. Theorem. So we extend it a little bit. And in particular, so what we did before, so what this H does, it sends Q to, it changes coordinates in the configuration space. So, but we have a configuration space, and a configuration space is essentially coordinates of all material points. So, but we also have time. So, what happens if you change both coordinates and time? So, let's assume they change coordinates and time some way. So, the question: can you have the same concept or not? So, we will consider space-time transformations. Space-time transformation, which means that we had generalized coordinates in time, and we want to define new ones, generalized coordinates, new time, in a general way. So how you do this? Okay. So anyway, where this transformation will live? So the Q lives in M, right? And time in real space. Okay, so this we call M1. So in a sense, in that sense, we will have a transformation from M1 to M1. So extended version of the manifold. So this is configuration space, and this is time. So we have M1, which is takes time also, includes also the time. And okay, so we can do it just exactly the same, very similar way for the coordinates. So we take coordinates Q prime S HS, but now we can put time inside. And in the same way we change time. T prime, let's put 0 as coordinate. So the this is vector, right? So this is n-dimensional vector, so we can just write it as component-wise, n component. It's n functions inside, and we put one more function which changes time. So this is it. Well, practically what you do, you have coordinates and time, and then you kind of define new coordinates. This is new time, this is new Q. So new coordinates. So we had time and Q in one way, and now we want to say that I want to define time and Q in a different way. So what we certainly need is that these coordinates are well defined. So what we need is that HS, H0S. So this is now from M1 to M1. So it should be diffeomorphism. Remember, so what it means is that it's one-to-one, so it can be inverted, and the functions are differentiable and inverse also differentiable. So we can all make all this analysis there, and also we assume that it's a group. It's a group structure. Group structure is just the same as we had before. So now if you take so if you first make the transformation with parameters S2, and then again making one more transformation with parameters S1, it's the same as making just one of them, but in the parameter S1 plus S2. The same thing. So the parameter S should be defined in such a way that transforming once with one parameter, another second time with new parameter is the same as transforming just once with parameter S1 plus S2. And of course, we want to have a continuous group, so S should be a real number. So so we defined what a transformation is, what the group is. So what remains is to see, can we define the symmetry concept. So what means symmetry? So what means symmetry in that case? So what symmetry means that something remains invariant, but now if you just say that Lagrangian will not change because you put t prime, it will not work. So we need to do something more, and if you want to understand how to do it, so we should go a bit one level up and remember that our equation of motion comes from the action. So let's remember what action is. So we had an action which is integral over interval of the Lagrangian function with respect to time, and it takes minimum on physical trajectories, or true trajectories, with fixed point at the end, at both ends. So you see now, when we were changing q and q dot, it was more like changing parameters in the integral. But now we change also q, q dot, and t. So we change also the integration variable. So what is the way we will proceed now is we kind of try to take this situation when we change time and q and reduce it back to the situation when we don't change time. So we make some trick which kind of reduces this situation to the previous one. So we define new variables. Kind of new generalized variables, the fake ones, so they have they will not have a physical meaning. So it's we say q capital. We call it q. So essentially, what we do. Let's do it like this. So we no. So the small q we call big Q, and big Q0 we call t. So we now consider time as a new variable, generalized variable. So so the generalized okay, the new, let's say, new generalized coordinates. So we call new generalized coordinates as a vector of QQ0. It's will be in M1, such that Q is Q and Q0 is T. Okay. So now say that this is in fact our new generalized coordinates. So if we call T a coordinates, we need to define time. So and new time. We will not even tell what it is. So in that case, the system is given by this dependence. So tau 0 defined on tau, q defined on tau. So tau is kind of fake variables, but as soon as we have these two functions with any dependence on tau, in arbitrary way, we recover. We just say this is time. This is implicitly this is time. This is q, and we recover original variables. Right? So actually, dependence on tau doesn't matter, because the really what matters are the values. Okay, so so now let's rewrite the action in new variables. So what you do first? So what we need is this is q0. This is q capital. So we need to write what is dt and what is q dot. So dt is d q0 of tau, and you just differentiate it. So it's Q0. Let's write, I will write dot as the derivative of tau over Q capital. So it's clear that it's over tau. Just I will even write this dot with a hole. So it means, oh, okay. So d theta d tau. And this I will just call theta 0 d tau. Okay, and then Q dot. How you define Q dot? So let's differentiate dq. Okay, Q derivative with respect to tau. How it can be written? So we can write it as derivative of Q with respect to tau, because Q capital is just Q, but this is function of T. So we need to use the chain rule. So it will be dq dt, dt d tau. Now we remember that this is Q dot. And this is Q0 dot. Okay? Because T is Q0 d tau. So we find what is Q dot, small q dot. Good. So we can write a new action. Action in new variables, we just rewrite the same expression, but in new variables. So it will be the same L. Instead of T, we put Q0 with Q capital. Then it will be this dependence. And then there will be dt, which is this stuff. And it's just the same S, so it should attain. This is just the same S, and there is direct correspondence between trajectories. So if this takes minimum, this also takes minimum. But if you can see that this takes minimum, but this function, which we call L1, it now doesn't have time. It depends only on derivatives. So if we formulate symmetry, so we can formulate symmetry for this equation using Newton's theorem, and then come back to the original variable. So that's an idea. So we have L1, which we define as L, which was original Lagrangian, yeah. Okay. So now what is symmetry condition? So now the change of variables. That change of variables that we had before is now really change of just generalized coordinates. From M1 to M1. And what it does is that Q prime equal HS Q0 and Q0 prime. So that's variable, since we called it small q by q capital time by q0, so this is just new change of variables, normal variables here, not time. There is no time change anymore. And we just say that this transformation is a symmetry if it does not change that Lagrangian. So the symmetry conditions. Symmetry condition is that Lagrangian in original variables L1 equal Lagrange. It does not change as you move to new variables. I'm mixing them. That's it. For the change of coordinate that we did before. And we have, and if this is true, then we have also Noether's theorem. So Noether's theorem gives us a conservation of the conservation law for the quantity which depends on these variables. And it's defined by the sum. Now you see index goes from 0 to n, right? Not from 1 to n, from 0, because we have also 0 component. dL1, dQi velocity, dHi, ds s equals 0 is conserved. So we have a formulation. So now we have to write it back, go back to original velocities in time, and see what does it mean in original velocities in time. So in original variables, space, time. Okay, we just have to. So first, let's write what this mean, what this condition means. So what means the symmetry condition? So let's just write this condition. We remember what is L1. L1 is L by Q0 dot with this variable. So let's put it inside and just compare. So the left-hand side will be Lagrangian, which is an original variable, just what it was. And then there was a Q0 dot. Q0 dot is Q0 is time. And dot is tau, d tau. So this is L1 Q0 dot. Q0 is time, and this derivative is with respect to time. And right-hand side will be L T in new variables after the transformation. So it's all primed. Prime, Q prime, Q dot prime. And now also there will be primes here, but no change in this tau does not change. We only change variables. Yeah, so this is L1 of 0 prime. Q0. So let's put it on the left. So remember, so what will come here? So it will be dt prime, d tau will be divided by dt d tau. And remember from the calculus that this is dt prime dt. So the symmetry condition is that original Lagrangian should be the new Lagrangian after the change of time and generalized variables by this extra term, multiplied by this extra term. So that's a change. So in previous case, we did not have prime here and no term here, because when t prime is t, this is just 1. Yeah? But when time is also changed, this means symmetry. Symmetry means that we change Lagrangian by that factor. Because essentially, it's not Lagrangian that we want to preserve, but action. And this factor comes from the change of time in the action. And now the conserved quantity can also be derived. So we need to derive conserved quantity. So we have this. So we need to see what this term is. dl1 dq I dot. So let's compute this one by one. So dl1 first let's do it for I equals 0. dq0 dot. So what it is? So it's derivative with respect to q0 dot from L1. And L1, and now let's put L1 from here. So take this expression, put them. So we have L1 written in terms of the Lagrangian. So this is L, Q, 0, Q. And then there is this fraction, Q by Q0, Q0. So differentiation, this derivative, it appears, this variable appears in into places, here and here. So there will be two terms. So when you differentiate with respect to Q0 dot, you just have L. Right? And then you have to differentiate with respect to this variable, which is called Q dot, right? So you have to differentiate with respect to all components which stay here, and then the denominator. So it will be plus. You differentiate with respect to all components. Then you differentiate this with respect to Q0 dot, which gives you minus squared. The second derivative of the denominator gives you minus squared. And then there is still that extra term left. So now remember, this is T, this is Q, this is Q dot. So we have dl1 dq0 can be written as can be written as L will be minus so what it will be, let's just write what this will be. So this will be minus Q ith components point divided by Q0 point, and this is minus Qi derivative. Right? So this will be minus sum dl Good. So this is hard part. So the second part, which is much easier, so we have to differentiate it with respect to other components, so I from 1 to n. So this Qi only comes here, and this you see that this is just it only comes here and only at each component. So it will be just simply dl dqi dot. And then there will be derivative. Denominator will cancel with the other one. That's it. So let's write it down. So remember, I use this dot is with respect to tau, this dot with respect to time. It's just same notation, but times are different. Just let's make it short. Okay, so now we have all derivatives, and I will just put them back into this condition. And now I have to distinguish between 0 and 1 to n. So 1 to n is one expression, 0 another expression. So first, so we have a conserved quantity, which I now can rewrite in original variables. So for 0, I have this expression, right? So L minus by dh0 ds. And then all the rest of the sum, so sum from 1 to n. And this is it. That's it. So this is an extended version of the Noether's theorem when we have symmetry of space-time transformations. You change space and time. If we're lucky that this transformation of space-time keeps the changes Lagrangian just by this factor exactly, then we have the conservation of this quantity. Well, something heavy. So this is, you see, so this is what was the old term. This is the same term that was in Noether's theorem before, and this is a new term. This is because of the change of time. Okay. So we actually did much more than we need, actually, for the application that we have in mind. Exactly for the time homogeneity condition. But I think it's interesting to have a more general form of the theorem. So now we make an application. So application will be about the conservation of energy.
Só isso eu entendi. Você supôs simetria no espaço-tempo e isso implicou uma mudança da Lagrangiana.
Eu fiz transformação de forma que agora é só transformação do espaço. Que situação de espaço-tempo que estava original, agora só é transformação de espaço. Agora, com a só transformação de espaço, eu posso usar termo de Noether, porque tudo já foi desenvolvido. Eu fiz tudo, e agora, como eu tenho condição e conclusão, eu posso reescrever tudo em coordenadas originais, onde é as translações de espaço-tempo. Good, no? So we apply now this. We apply this formula, conservation of energy. And here we just recall that there was one of the symmetries of the system that we imposed from the very beginning. It was homogeneity of time, which is part of the Galilean group. So this is a transformation which changes time, t to t prime, which is t plus, let's put s here. It was t0, we can put s, where s is any real number. So we can change time without changing coordinates. So we just only we measure time from different origin. And this means that, in particular, all coordinates of all the functions, all the material points do not change. So whatever generalized coordinates you put, you can just keep them the same way, but change time. So this is space-time transformation. So this space-time transformation where so writing it in original form, so H0s is just t plus s, right? So this is new time. And q prime, which was hs qt, is just q. So this is trivial function. It does not change. Okay. So what we have is that, of course, dt prime dt is 1. Right? 1. And it means that so symmetry condition, this is 1. So what we have on the symmetry condition, so symmetry condition is that L T Q Q dot equal L. So new time is this. Coordinates velocities do not change, and the cofactor is 1 for any s. And you just see that this for any s means just L does not depend on time. Remember what we did in the first step. So the Lagrangian, this symmetry implied that Lagrange does not depend on time. So symmetry condition is satisfied for any system where there is no time in Lagrangian. So time, there is homogeneity of time condition. And now the Noether's theorem gives you the invariant. So we call it E. And we take it as this C, but with negative sign. Because if plus C is invariant, minus C is also invariant. So what do we have? So you see, so HS is does not depend on S. So this will be 0. Okay. This will be T plus S. The S will be 1. So all what will be left is that part. And to take one, so we change the order of these two terms. So this is called energy. So energy is an invariant which comes from by the Noether's theorem from the homogeneity of time. So if time is homogeneous, then the variation principle implies that, with Newton's theorem, implies that there will be something is conserved. We call this conserved quantity energy. And now let's see that this is exactly the energy we're used to. So remember, let's take system of, for a system of material points. No. Recall a general form of the Lagrange. Remember, for a system of material points. So what was Lagrangian for the system of material points? It was kinetic energy minus potential energy. So you already see there is no time inside for an isolated. No? So just a system which contains all points which interact. So there is no time. So automatically we conserve energy. But we know a bit more. We know that in generalized coordinates, we know also this that kinetic energy, if you remember, we wrote the general expression for it. It's half over sum over two indices going from 1 to n, and then there was a coefficient. Let's write it jk. We will need it. By qj, qk. So we had this expression derived. If you take original system of point masses with velocities, coordinates, and then you write it in terms of generalized coordinates, this was an expression where this coefficient, we had the expression for this coefficient. What will be important, we saw that they're symmetric. So if you change indices, it's the same thing. So now we can write what is let's see, what is the energy? What is the energy for this system? So we use this condition. So in order to write energy, we need to compute essentially this term. So let's compute this term. So this term, so velocity only appears here. So it says dt dq I dot. And then we differentiate all this expression. So it will be 1/2 d dqi. So we need to find where this velocity appears. It can appear here when j equal y, and it can appear here when k equal I. So there will be two terms when you differentiate the first and differentiate the second. So when you differentiate the first, you just remove it and put j equal I. It will be half of the sum of the remaining variable. And instead of j, we put I. And it will be k. So this will be first. And the second will appear here. So here we put j equal I, and here we put k equal I. So the second sum will be 1/2 over j from 1 to n, m j I q j. Two sums. So now there are separate sums. So we can rename this k, say that just instead of k, write j. Doesn't matter. So we rename k to j. So it'd be m I j q j. Another sum m j I q j. But these are the same thing because mass, generalized mass is asymmetric. So this is equal mij. So essentially we remove half. And I also want to call ji. Oh, okay. No, ji I cannot. J. J. M I J Q J. Okay, so we have this coefficient. So what remains is just substitute. So the energy is what? So let's repeat this expression. So it was sum over I from 1 to n dl dqi dot qi dot minus L. So now we use that sum in that place. So it will be sum over I and the second sum over j. So we put them together. Then it will be mij. I don't write the argument. Okay, let's put q. Then there will be qi and qj from the other term. So it will be qi dot qj dot. So this is it. Then what is L? Minus L. L is t minus u. So with another minus, so it will be minus t plus u. But now you have to see that this is actually 2t by definition, exactly. Because kinetic energy is this expression by 1/2. So that means that we found that energy is the sum of two energies. So this justifies why we called T kinetic energy and potential energies, because they just take two pieces of the full energy. So this is total energy. Okay. Again, as I said before, you can, in principle, in order to show that energy is conserved, you take this expression, substitute into the take derivative in time, use Euler-Lagrange equation, you just find directly that it's conserved. But we did a longer way, but it's conceptual way. So what we said is that not only if you change generalized coordinates, you can have the relation between continuous symmetry and conservation law, but also you can also have this relation if you change generalized coordinates and time. So you can make more complicated transformations. We still can give a meaning to what is symmetry, and automatically we have to give a meaning what means corresponding conservation law. Yeah. So derivation was a bit tricky because we made a trick so that we reduced it to the previous case where we only change coordinates. And the main application of the whole series of this idea is that we connect the homogeneity of time to the conservation of energy. So conservation of energy is a consequence of homogeneity in time. So automatically, I mean, the message is that you look at the Lagrangian. If Lagrangian does not depend on time, you have energy automatically. There is a formula. And in a situation when there is a time in the Lagrangian, and we had this example when the pendulum with vibrating support. If you write Lagrangian for that system, time will be inside. So automatically you know that energy cannot be conserved in this case. So you don't need to. So that's kind of symmetry considerations that they can help you to figure out rapidly which conservations you do have, which you don't. And this is we will use on the second half of the lecture to solve one of we'll solve the Kepler problem. We'll see how the Kepler problem, we already wrote equation, so it's equation for the two-body problem. So two bodies with a gravitational interaction. And there is an equation, but that's complicated equation, and we'll see that you can solve it conveniently just using conservation laws, so without using equation itself. Okay, so coffee till break. Funcionou, não? Obrigado. Okay, so let's solve some practical problem. So this is a Kepler problem. Which is just two-body problem. For special type of interaction. So we already considered what it is. So we considered two masses, MA and B, and they interact with the potential depending on the distance. So this is gravitation. This is gravity. So the gravitational interaction between them, where the r is distance, and k is just coefficient, which is well, physically it's a product of masses by gravitational constant. So we already considered this problem, and we found that the Lagrangian function can be written as in generalized coordinates. So m over 2 over the velocity of the center of mass squared plus reduced mass over 2 relative distance squared, and then minus or plus k over x. So this is what we wrote last time. So this x. So remember that x is the difference, the distance, the relative distance, and r is the center of mass. I will not write expression for it. Okay, and then since the interaction part only depends on relative distance, so the center of mass moves with has a uniform motion with constant speed in constant direction. So this gives you there were two equations. So one is r double dot equals 0, and another equation was that x double dot was minus k over m x cubed. So this is so the first equation has a linear solution, is easy, but this is not. So we want to solve it. And of course, what's clear is that this equation is this is Euler-Lagrange equation for the Lagrangian, where you just remove this part, right? So, because when you write Euler-Lagrange equation, you only keep the term which depends on x. Okay. So that's not that simple equation, because x is a vector. So this is second order equation in three-dimensional space. So it's not so simple equation. It's not actually, if you just go straight, it's not so simple. Okay. Well, not impossible, because we actually know how to solve it. So this is a relative motion. Good. So symmetry. So let's see, just see continuous symmetries. So let's try to see what are the continuous symmetries of the Lagrangian. So first, and we make a list that we used to. So the translations, rotations, and so on. So translations. Translation means that x goes to x prime, x plus x0. So this is certainly not a symmetry of the Lagrangian, you know, because because of this term, because it's not. So if you make translation in, you cannot translate relative distance. So this will not work. So we don't have conservation law for translations. And actually, this is because we already use this conservation law for the other variable. But we still have rotations. Yeah, we can rotate x, and rotating x does not change Lagrangian because it's only norms are staying here. Yeah? If you rotate, norm doesn't change. So this means that we have a conservation of the angular momentum. The angular momentum, which is, we know also expression for, what will be expression for the angular momentum? It's mx cross x dot is conserved. And we have time translation. So this was space translation. This was space rotation. Now we have time translation, which is also yes, of course, and because L does not depend on time, so translating time does not matter. So we have energy. And energy, we also know that this is potential. Kinetic energy is potential, so for energy we change sign. That's already quite a lot, because you see how many equations. So we have three equations of second order. Essentially, it depends on 6 unknowns, if you remember differential equations. And we have four conserved quantity. We have 4 components of the angular momentum and 1 energy. So out of 6 unknowns, we already have 4 constants conserved. And actually, there are 5, because there is one more conservation law, which is exactly specific to this U, and gives you one more conservation law. I will not touch it here, but if you're interested, you can look at it. Actually, there is one more conservation law, which is responsible for the fact that in a relative motion, if the motion is finite, they always come to the same position as they started, periodically. And this is only true for this Newtonian interaction. If you put another power here, the planets will not come to the same position. They will just stop. No. So there is one more conservation law, but we don't need it. We will just use these 4. Okay. So the first is, so let's start with the angular momentum. So you see that if m is conserved, then, and this is cross product, it means that velocity is orthogonal to this vector m. M is fixed, so velocity is always orthogonal to m, which means that motion is always in a plane orthogonal to m. Right? So that means that the motion is confined to a plane orthogonal to m. And this gives you convenient form how you can define coordinates. So let's put x3 coordinate along vector m, and then there will be x1, actually x1 should be here, x2, x1, x2. So the x1 is 2 plane. The plane of motion can be x1, x2, and so the motion is in this plane, which is orthogonal to M. Okay. So the motion occurs just in coordinates x1, x2. This is our point. So actually, it's not 3-dimensional motion; it's 2-dimensional motion. And another thing which is convenient is, since we're on a plane, we can use polar coordinates. So we just use distance rho and angle phi, polar coordinates. So this will be our new generalized coordinates, polar coordinates. So remember what it is. So it defines x1 as rho cosine phi, x2 equal rho sine phi. And we need the velocities also. So x1 dot equal rho dot cosine phi plus rho phi dot minus sine phi. Okay. So we already know that vector M is along third coordinate, so the only non-trivial component is M3. So M3. So let's compute M3. M3 is, remember, so it's mass by the third component of the cross product. So the cross product third component is x1, x2 dot minus x2, x1 dot. So this is constant. And so let's divide by M. So M3 by mass, by this reduced mass, is x1, x2 dot minus x2, x1 dot. And we put now these expressions. So it will be rho cosine phi by x2 dot minus rho. Okay. And so what you can see is that this is what must happen. So this term cancel with this term, because this is sine cosine, rho dot, rho dot. It will be rho squared 5 point cosine squared plus rho squared 5 point sine squared phi. And now sine squared plus cosine squared give 1. So remember, so phi dot is derivative with respect to time. So let's write it just openly. And rho squared we can move to the other side. So we have this relation. So the change of angle, you see change of angle, when you move, the change of angle, it only depends on how far you are. Okay. And let's see that this is actually a famous law of equal areas from Kepler. So imagine that you have some orbit. So the rho is distance. And let's consider the small change of time. So very small change of time. So in the small change of time, the angle changes a little bit. So when the angle changes a little, we can compute this area. So this area is rho squared by change of angle divided by 2. This is triangular. The change of the area is rho squared by 2, change of the angle. Which means that if you want to see the rate of the change of the angle, to derive it with respect to time, this is rho squared over 2 d phi dt. The phi dt we know. And distance cancels. So we have the change of the area is constant. And this is what's called Kepler's law. Of equal areas. So you can say that areas swept. If you look at the vector which connects 0 to your point and see what is the angle, what's the area this vector will sweep. So and then this the area is swept in swept at equal at r equal time intervals. So if you look at the vector, and it's sweeping at some time, in a certain time interval, so it will be constant whatever time interval you take it for the equal time intervals. So that's one of the results which is in the very basics of which give rise of the classical mechanics, and it was discovered by Kepler from measurements. So he was looking at the planets, computing the things, and he discovered this law. So this was one of which later led to the Newton's law of motion. Okay, so this is first result, and we derived it, as you can see, from the symmetry of rotation. So rotation, which gives you angular momentum, and this gives you the Kepler law. Okay, so the next is we have one more conservation law, which is energy. So let's see what energy gives you. Energy. So energy is let's write it what it is. So energy is mass. So we're in a plane, so it's x1 dot squared plus x2 dot squared, and then there is potential energy plus k over plus should be minus, no? Where's yeah, minus. Potential energy negative. Minus k, I already write it over rho. And now we have to write this in polar coordinates. So let's use these two expressions. So it will be m. So the square of the first will be rho square cosine square phi minus 2 rho dot rho phi dot cosine sine. Second gives you, so this is dot here. So you see, this cancels, and here cosine plus sine give 1. So it's m rho square squared, or dot squared, plus rho squared phi dot squared. Let's give rho. M. Okay, that's not it, because phi dot derivative of angle we know. So it's m rho squared, and then square of this whole stuff. So we can cancel one mass and two powers of rho. So it gives you this expression. So we have energy. So final expression is that energy can be written in the polar coordinates as a term which has exactly the form of kinetic energy, right, with respect to distance, and plus some function which we call effective potential, which is a rest. It only depends on rho. So it's what? It's this, the last two terms which are there. So it's m free squared over m squared minus k over rho. Okay. So now if this is in fact, so this is constant. So energy is constant, so it's given by initial position and speed. This is known function, which also depends on another constant, which is given by initial state. So we can solve this equation. So what we do, you derive, you express velocity from this formula. So rho dot squared, which is remember it's d rho dt squared, will be m over 2 e minus c. Okay. Now I take square root. But square root, we don't know sign. And in fact, sign can be both positive and negative. Okay, the next what you do, let's put dt on the other side and this below. Good. And we integrate. We integrate from some initial distance, initial point to a point that we're interested. So the right-hand side is t minus t0. So what you have, we have some function of distance, which is, if you succeed to take this interval, this will be function of distance as in the right-hand side time. So this is a solution, just given in implicit form. So this is implicit form of the distance as function of time. So we have function of distance here, time on the right-hand side. So if you this can be in principle solved, and we will solve it, and right-hand side time. So it's you cannot. Well, so that's in principle already a solution. So it's possible to write to solve it completely, if you know how to integrate this expression. Then you can solve it completely, but we will not do it. So actually, what is our interest? In many books, you can see if you like. What is our interest is a form of trajectory. So let's what is a form of trajectory? So form of trajectory. So what is the shape of this point that is given by, that is traced by the relative distance? So we want to know what is rho as a function of phi, of angle. Well, just to say, so here with this integral you get form of the distance as function time. Then if you solve it, you can put it here and solve it with respect to angle. So in principle, you can solve everything explicitly, and this is solvable for the two-body problem. It's not solvable for three-body problem, but for 2D problem, it's solvable. So for us, what is more fun is to find form of trajectories. So how you derive form of the trajectory for this function? So let's use this expression here for d phi dt, and I will write so that change of angle is m3 over m rho squared change of time. But now dt I know from this expression. dt is d rho over this into 2 over m. It's not 1 over 2, it's 2. So this is You don't find my mistakes. This is not good. Okay. And then we put it there and put the rest on the other side. So flip this. Okay, so that's a form equation for the trajectory. In principle, plus and minus, plus if it goes in one direction, minus in another, so let's just take plus. And then you can also, this is just very technical, so but direct. So you can, what you can do, you can now use this formula here and transform it to the right hand side, which has this form rho square over p. You can check it if you like. So e squared minus 1 minus p squared over rho squared minus 2p over rho. And here p is parameter which is this. E is square root of 1 well, some working a little bit with this formula, you just put it in that form. And another exercise you can do is you can check. So it's not trivial to solve this equation now, but the solution is known. So solution, well, I'll give you a particular solution. Well, it's almost general solution. So it's P. Actually, it is. I will write it in general form. 1 plus E cosine phi plus phi 0. So for arbitrary phi 0, arbitrary phi 0, we have this. This is a solution. If you like, you just put it inside and check it satisfies the equation of motion. So I'm kind of jumping the technical derivations, which are certainly not our goal to do in this course. But you can do it. So this is actually one of the few non-trivial problems in mechanics which can be very, very, very fundamental, which can be solved completely. And this is what gave rise to the, well, directly connected to conical section, because this is conical section. So what is this? What are the solutions? So the solutions, they certainly depend on the value of E, because cosine cannot be bigger than 1, right? Between minus 1 and 1. So if E is smaller than E is positive, it's square root. So if E is between 0 and 1, this is never 0. Yeah, so it means that the distance never becomes large. So we have a confined motion. The two bodies do not come close. If E is 1 or bigger, then this value can be 0. It means that there will be separation to infinity. So that's 3 solutions. And moreover, you can see this fact from well, another view on this of this difference you can see from the plot of the effective energy, which depends on distance. So you see what it is. So it's positive coefficient divided by rho square minus coefficient divided by rho. So when rho is small, this is main term because it's square. So when rho is small, this term dominates, so this term is plus infinity. So for small distances, it's plus infinity. For very large distances, this term is smaller. So this is the main part. So and it goes to 0, but from a negative side. So they connect like this. So this is the form of the effective energy. It has a minimum. And the central, so there are three cases. Energy equals 0. Energy is positive. And energy is negative, but above minimum. So let's consider these three different cases. So first is energy is negative. So you see, if the energy is negative, and energy is a sum of effective and kinetic, but kinetic is positive. So it means that energy can be certainly above, energy cannot be smaller than effective energy because it's plus something positive. So it means that we are restricted to between two distances. This is the smallest distance that we can get and the largest distance we can get. And in fact, in this case, the motion is ellipse. So so we have elliptic motion. Ellipse, and this exactly corresponds to the situation where E is between 0 and 1. So this is formula for the ellipse. So next is energy is exactly 0. In that case, you see, in that case, we have a motion between some minimal distance, and it is not limited. So this is a parabola. And finally, for the energy positive, well, it's the same situation. We have a minimum distance, and then the motion is unlimited, so this is hyperbola. I'm not giving you details of the computation, but that's already known thing from analytic geometry, which is another field. So what is important is that we derive the equation, and this equation has a solution which is a classical solution for the conical sections. So depending on E, which is eccentricity, you get or the same thing, which is depending on initial energy. You have either limited motion which is along the ellipse, or parabolic or hyperbolic hyperbola. And you can see that at no moment we actually used equation of motion in this case. We only used conservation laws. Conservation laws, and this was very convenient. Of course, generally you cannot do it, but in general, conservation laws still help a lot because this decreases number of equations that you have to solve. Every conservation law decreases the number of equations you have to solve. Yeah, so conservation laws are very fundamental, and we essentially listed all the conservation laws. So every symmetry which is inside the Galilean group gives us conservation law, except for the main symmetry, Galilean transformation itself, going to the moving frame. And going to moving frame does not give conservation law because it's not a symmetry in the sense of the Noether's theorem, because it does not preserve Hamiltonian or does not preserve Lagrangian. It just preserves Lagrangian up to the additive part, which is preserving equation of motion, but not enough to have conservation law. And all others, so that homogeneity of time gives you linear momentum, conservation isotropy homogeneity of space gives you linear momentum, isotropy of space gives you angular momentum, and homogeneity of time gives you energy. So these are basic conservation laws which are related to symmetries. And every moment you have breaking of any symmetry is automatically that you don't expect that you automatically expect breaking of the corresponding conservation law. Yeah, so that's how you can see it directly without without actually analysis of equations. Okay, so we're done. Tomorrow I expect to give you one more exercise, but not to end of this week, the next week. Just to be anticipating to give you more time. And we can. I have to give the email for the monitor. I will put it in the web page. So I forgot to do it so far, but tomorrow I'll do.
Why in the situation where energy is greater than zero, we have a hyperbola and not a parabola?
Well, that's the solution. So it's known that in case of energy zero, you see energy zero, eccentricity is 1. Yeah, so that's it. So it comes from energy is positive, eccentricity is bigger than 1, energy negative, it's smaller than 1. So it's direct connection. Okay, thank you. So, ciao, tomorrow.